क्या कपड़ा
गंदा बना होता है।
अभी भी कर दो, अभी टाइम है,
अभी नहीं, अभी नहीं, अभी नहीं।
एक 1.5 मिनट लगेगा वैसे।
Hello everyone, welcome. Hello everyone, can you hear me? Okay, welcome to this introductory session of Simba School, where we have Dr. Shaheen with us, who is going to deliver a series of lectures, which are really very important to cover all the basic necessary background for the Simba School, which will be starting from the next week. So, welcome to all the participants. I request all of you to keep yourself muted. And if there is some question, just raise your hand so that we can take your question. And Dr. Shaheen, during her lecture, she will take the pauses in order to see whether if someone has any question, and she will try to answer all those questions accordingly. Okay, now welcome to Dr. Shaheen.
Can you hear me? Okay, so let's start our first lecture, and what we will discuss is about the introduction to algebraic geometry. So I will start with this question, that what is algebraic geometry? Yes, please. Okay. So algebraic geometry is nothing, just a study of solutions of or zeros of polynomial. So for example, you want to say this question, that let's solve this equation, right? So you may answer this question, what is this equation means that, and what does it mean, how you will say that what is the solution of this equation. So this means that you need to find point x, y in some field or some space, let's suppose, which satisfies, let's suppose at this moment r square, which means that both are real, which satisfy this equation. X squared plus y squared is equal to 1. So this means that we all know about that one. The solution of this equation is nothing, just a circle, right? And similarly, we may ask this question, we can ask this question, what is this one in C2? It's depending, all the solutions are depending on the field or the, you can say that field or whatever you are taking the set or space in which you want to look the solutions of your equations. So more generally, we can ask this question that let's solve this equation. It can be consisting of lot of equations. So we need to solve these equations simultaneously. So you will say that let's solve this system like you solve a system of linear equations in linear algebra. Right? Over R or C. So let's say that our aim is to understand what does it mean? What do you mean by to solve a system of polynomials, polynomial equations? And if you can see that if this solution is finite, let's suppose we first of all understand what does it mean, the solution mean, and then we will ask this question, if this solution set is finite, then we will ask this question, what is the kernelity of that set? And then next question is, if it is not finite, then we will ask this question, how you can see this one geometrically. Right, so we will try to answer these questions in this course. Okay, so let me just start. Might be possible either we can have there is no solution of some equations or not. So, for example, if you will consider this equation again, let's say this one. Let's solve this equation. If I'll ask this one, solve over R. I mean, you need to find real numbers which satisfy this equation. So what will be the answer?
Solution.
There is no solution. Right? So first of all, we need to fix that thing that we need to consider our space such big that it may not have the empty solution set. It must have some non-empty part. Right? So, but we know that if we will solve this equation on our C, we know that there are two solutions. Right? So that's why we will consider our solution space is a part of depending on the complex number, not on the real number due to this reason, because this does not have any solution in R and this has solution actually in the complex one. So that's why let's fix no. First thing we need to fix that this is C, which means that K fix kar lenge and that will be just a field, which is the field of complex numbers. So throughout my lectures, we will always consider K is just a field. So I will write always as a K, but remember that this is always a complex number. And the reason is, as I said, because this has a solution because we know that by fundamental theorem of algebra, we say that every polynomial, every non-constant polynomial has every non-constant polynomial has solution, or you can say that roots or zeros in C. Of course, polynomial over C, right? Which means that the polynomial which we are considering, their coefficients are from complex numbers. So they always have a solution in C. So this is the reason we are considering here K is a complex number. Okay, there is a problem of resolution. Can you see this? Okay, so let me fix few more notations, right? So we'll always consider polynomial. The set of all polynomials in n variable, which is over K, it is written in this form. So if I am taking a polynomial, so if I'm taking f of xn is a polynomial of this one, this is a ring. So it can be always written in this way. Right? These are coefficients which are in K, and usually these are called in monomials, which are written in this form. Right? Okay. And there is another notation, which is because we want to see where our solutions are lying. That space is called affine space, which is actually this one. So this is our affine n space, which is nothing just the n tuples of numbers. These numbers are belonging to K. Right? So this is our affine n space. Okay. So now you have here something which is algebra. right? And there is something which is like we can say that some geometry because we want to look the solution in this one. And this is some algebra which is giving you the solutions of polynomials. So now you can see that what are the connection between these two things? Is there any connection between this polynomial ring and Kn? So yes, there is a connection because for any given polynomial f here, we can always define a map from Kn to K. So this polynomial is actually giving you a map. In actual, this is not a map, but every time you will consider a polynomial, this is always give you a map from Kn to K. And how it is defined? If you will just taking a point in this affine space, and then you will evaluate this function or this actually polynomial at that point, and definitely you will get the answer in K as well. So this is very well-defined map. So this is actually give you the connection between algebra and geometry. So for this algebra part, you are coming through this geometry part. So this is sort of giving you a connection between algebra and geometry. Okay. Now let me just go with the precise definition. These are just few notations. And now what I will define. So I will just define as I said before, because our aim is to study these solution of polynomials. So which means that we will just collect some collection of polynomials and then we will move to that one. Okay, so let's choose some polynomials. I'm here taking finite many polynomials at this moment. So remember, every time our affine space and our polynomial ring is always fixed. So whenever I'm taking a polynomial, then it is clear that I'm taking a polynomial in n variables, x1 up to xn, and the affine space, which is just a n. Okay, so if you have chosen some finite many polynomials in this ring, then we can define this one. So let me just first write this notation, and this is defined. This is nothing just the solution of these polynomials or the zero set of these polynomials. So you are picking all points. Let me just put here. So I'm picking all points in our space such that this satisfies these polynomials. And definitely this set is contained in Kn in our affine space. And this is known as affine algebraic variety. And in some books, it's also called affine algebraic set. But at this moment, I'm using this algebraic as an algebraic variety, right? So this is my algebraic, affine algebraic variety. So I'm just following that Little Fox has said in their book, this one as a variety. So I'm also going with the same notation and definition. Defined by these FRs, right? So this is also called the zero set. In some books, you can see the notation as Z of this one because of the zero sets of this one. And here we are just using this notation as V. So we know this one. Okay. So this is our affine variety. or affine algebraic variety, but on simple way, we will just call that one as an affine variety. Okay, now let's see some examples. As we have already seen some examples, but let's see here more precisely. So my first one is the zero set of this one, x square plus y square minus 1. And we know that this is nothing, just a circle. If we want to draw that one, because here we are drawing in C square, it's a complex plane, it's not a real. Lekin when we are drawing something, then definitely we are just looking as a R square. So we are just drawing this one, not in complex, right? Because complex plane is in usual as 4-dimensional piece, and here we cannot see that one. So definitely when we are just drawing these things, curve, something like that, so then definitely we are using R, this real numbers. So we know that this is nothing, just a circle. So now, what is that one? This is again a variety because it satisfies the definition of a variety. And this variety is nothing, just a cone, which we can, of course, is in the 3-dimensional. So this is like in this way, right? And the third one is if you will look, what is that one? Because this gives you solution in R3. If I'm, as I said before, I'm just looking the solutions in real space. So definitely this gives you some kind of a hyperplane, right? And this one is again giving you a plane, right? Both are giving you a plane, and but because here we need to see that the common solution of that one. So definitely what we are looking the common solution of those planes, which are or I will say that generally space because it's not really plane, because they are just like a curved surface, sort of a surface. So this gives you the intersection of that one. This gives you actually a curve, right? Which is 1-dimensional, which we will see what is the dimension of that one later on. So its curve is like in this way, right? Because this is a part, this is a part, and that is a part. Okay, so this is known as a twisted cubic curve. Okay, so now we have this definition. What we can do with this definition? So very first few questions. If you have two varieties, for example, you are given two varieties in Kn, then what can you say about their intersection and their union? So the question is, if you are given two varieties, what about their intersection? Is it a variety or not? What about the union of those varieties? That is a variety or not? So for example, I will say that the answer is yes actually. In both cases, answer is yes. Because you can see that if these are varieties, so this means that you will always have this thing. It is coming from some collection of polynomials by definition. Is it just a zero set of some polynomials? Right? And W is again a zero set of some other set of polynomials. I don't know they have some common polynomials or not, but generally they are different. So what will be the intersection? Can you guess? Because intersection means that you need to find the common solution. So the common solution is suggesting here that you are collecting all the polynomials in that. This means that this variety is defined by the all polynomials given these by Fi's and Gj's. Right? Because this gives you the all common solution given by these polynomials Fi's and Gi's. And now let's see what will be the union. So union means that, what do you need to know that? So union means that you are collecting all the zero sets from this part and this part, right? So which means that generally union will be that one, but we want to see that is it a variety or not, which means that it is coming from a zero set of some polynomials or not, then you can see easily this thing. This is nothing just equal to the product of fi's j's, where I is varying from 1 to f and j is varying from t to. Do you agree with that one? Okay, this union is nothing just this one. Because when you say that, if you will pick a point from here, which means that this is either here or here, which means that this is either given by zeros by this one or this one. So which means that if you will just picking an element from which is the multiplication of fi or fgj, that is giving you nothing, just the product, because it covers all this one. So this is, and this is really good. So if you have any questions so far,
I have a question. Like I was thinking it in the other way around. Like V intersection W is actually the product, and V union W is the connection of both.
so you are saying that this intersection means that this is coming from the product.
Yeah, that is written for U V union W.
Okay, so for example, if you will take an element from here, which means that product is zero, which means that either fi is zero or gj is zero. So this means that your element is either in V or in W. So that's why you are getting union here. And then you are saying that the common solution, which means that they should all satisfy at the same time fi's and gj's as well. So that's why it's a collection of all polynomials is coming in the intersection. For example, as I said before, where is that my example? Sorry, here is my example. If I want to look the zeros of this one, what does it mean? I will look the zero of this polynomial, which I said that this gives you a like a space of dimension 2. This is another one, a space of dimension 2, and we are looking here, both satisfy that one. That's why you get this curve, which is just a solution, which is just coming from the intersection of that one, which means that satisfy both of them. So both of them satisfy means that it must be the intersection. Okay, got it? Okay. Okay, so this means that so far we have the union and the intersection both are affine varieties. And now there is more general question. Can you take infinite many varieties and their union is also a affine variety? And infinite many infinite intersection is again an intersection of varieties is again a variety or not? So now we will try to answer this question. So, okay, so is there any question from the audience? Okay, if you have any question, please let me know. Okay, if there is no question so far, so let's move on.
We have a question.
Sorry, there is a question. Okay, Faira, please unmute yourself and ask the question.
Assalamu alaikum. So I have a question regarding the intersection of the varieties which you did in the last board.
Yes.
Can you elaborate that, because the intersection is not that clear to me?
Okay. Okay, as I have already suggested this one by using this example. For example, here you have two polynomials, right? You can see that one. And we are looking first of all the solution of this one. Can you tell me what is the solution of this one? This is a hyperbolic plane which is coming in the direction, right? And this is a curve which is in y-axis is going along that one, right? And now you need to see the intersection of those, because we are looking the solution which satisfies this equation and this equation. So that's why we are collecting all those solutions which satisfy both of the equation, which means that we are considering all those solutions which are coming in both varieties. So that's why you are getting here the intersection is coming through all these polynomials. The collection of all polynomials which you are considering in your corresponding varieties. Is it clear to you?
Yes, thank you very much.
Okay, now I'm extending my question to infinite union and infinite intersection. So which means that I'm taking the infinite many varieties and then taking their union and intersection. So what do you think? Which answer is very easy to say? So infinite union, this is big no. It's not always an affine variety. And we will give you an example in a moment. And this is yes. And let's see why this is true.
And when we
Okay.
say infinite, does it mean countably infinite or it can be?
Infinite. Infinite. It is either countable or uncountable. Right?
Right.
So there is no restriction on that. When you say that infinite is not saying any other thing, then definitely infinite means either countable or uncountable.
Can you give example that infinite intersection is not only zero?
Sorry,
Infinite intersection of varieties is not only zero. Can you
is not
only zero?
only
Zero.
zero. Okay, let's see. Okay, so to come this point, let's consider something to answer this question. Let's take any set of polynomials. I'm not putting any restriction on that one. On this set, there is no restriction. It could be whole set of polynomials. It could be finite, it could be infinite, or whatever you want to take. So arbitrarily, you have chosen this set, right? And now what I will do, I actually define a variety corresponding defined through this set, which is nothing just this one. So you are putting all those points in your affine space such that f of f all polynomials which are in your x, they are satisfying this one. Right? So this is again a zero set, this is again a affine variety, but defined by S. And here is no restriction on S. It could be infinite one.
Any arbitrary set of.
Yes. But let's see why. Why this is also defined by just a finite number of points as well. Okay. So one more thing you can see that if here on S we don't have any algebraic structure. S does not contain any algebraic structure, but we know that we can put an algebraic structure on not only S, but we can extend that idea. We can just consider this ideal which is generated by this polynomial S. So this is the smallest ideal which contains S. S not necessarily to be an ideal, but here we are considering the ideal which contains S, and this is the smallest ideal. And interestingly, you can see that this thing that the variety of this I, because I contains lot of polynomials more than S, but it's same as this one. Do you agree? This is which one is very trivial? Which set is bigger? This is always in I. So which variety is bigger? It's opposite, right? So I will write here one more property. If S is contained in S1 is contained in S2, then definitely the variety of S1 is bigger than variety of S2. Agree? Because here the points which are satisfying this relation then that definitely satisfy these polynomials as well. Because S2 contains S1. But the other way around, definitely not true. Because of, again, if you, I will go with this equation, this example as well. So as I said that this is giving you a whole plane. But if I will just consider this one is as a S1, which contains just single this polynomial, and this S2, which contains these two polynomials, then definitely the variety which is defined by S2, S1 is more than this variety which is just a curve here. Okay, got it? So definitely this is very much clear that because this is a bigger one, so it always contains here. And why this is true? If I will pick any solution from here, this set, then definitely it will be here. Can you guess? Because when you are saying that, if you are picking any element from here, because ideal, we have made here ideal, which contains all the sum and the scalar multiplied, or the sorry, scale not scalar, the product of the polynomial is this one. So, for example, if n f x is in I, then definitely this is in I, and for any other arbitrarily G and H is in I, for all H belongs to this polynomial. That is the definition of ideal, right? So that's why you get both are certain, because if something is 0 here, then definitely it will be 0 here and here. And something is 0 here, then either it will be 0 on G or on H. But if you are picking an element from this set, then definitely they will be here. Okay. Now, and let me just write here, this is just the ideal generated by S. Okay, here I will use a mean result of Hilbert, which is known as Hilbert basis theorem. This says that actually every polynomial has only finitely many generators, which means that every ideal in your polynomial ring is generated by finite many polynomials. Right? So let's recall that one. Hilbert's basis theorem, which says that every ideal definitely is an ideal, proper ideal, because it's a sorry, it's not non-empty, but you can say every ideal here is finitely generated. Which means if you will pick any ideal, then definitely you can always find a finite many points or polynomials in your polynomial ring such that that ideal is generated by those polynomials. So from here, let's come back to here. So this means that because of Hilbert basis theorem, I can always find a finite set of polynomial which is generating this one. So this means that this is nothing just equal to this one. Let's call F1 up to F2. Okay. And this shows that actually infinite intersection is just a valid again. Because here you can have infinite many polynomials. Of course, I also contains infinite many one, but this has just the finite. Because every polynomial, what does it mean? It means that if you will pick any element I, then it can be written as the H1, F1, HF, Fs. So every element in your ideal can be written in this way. So that's why you get this result. using Hilbert basis theorem. Okay. So this answers our question that the infinite intersection is all of a affine variety is always finite or always affine variety. And here, I mean, affine variety means that that is always a zero set of finite many polynomials. Yeah, there's a question. Sorry. Yes, it's any polynomial with n determinant. And k is here, definitely here we are considering field. And if it is not a field, then we can consider the polynomial over Noetherian ring. And because our K is a field, so it's automatically is a trivially Noetherian ring. Or Noetherian means that it has the same property. Every ideal is finitely generated. So answer is yes, if your polynomial ring is based on field or on the Noetherian ring as well, generally. Okay. So now you can see that what we have done so far. We pick arbitrarily set from our set of polynomials and associate to a set which we will call the zero set of those polynomials. So actually, this set is just defined by this ideal. So I can say that for every ideal, I'm assigning a variety, right, which is in our affine space. So now you may ask this question: can we have arbitrary set in our affine space? And can we associate some special ideal corresponding to that set or not? So answer is yes, we can do that one. And that is called the ideals. So for example, I'm picking a subset of Kn, affine space, right? And now I'm defining this ideal of A, which is actually ideal of A, which means that it will be a subset of your polynomial ring. So I'm just taking all polynomials in my polynomial ring, which satisfy that f of A is equal to 0 for all A belongs to A. So here, let me just pick this notation. Can you go with that one? So this A is nothing, just the n to 12. So I will use this notation as well, right? So my ideal is actually consisting of all those polynomials where those polynomials are zeros on this set, right? So this is really an ideal. You can check this one is indeed an ideal. So I'm not going to this one, do here, but you can check as an exercise. You can easily see that if you will pick two elements from here, then definitely you will add them, they will be 0. So addition at that point is 0 because it will be splitting those polynomials. And similarly, the product as well. Okay, that's great. So now what we have? We have two things. From a set or from an ideal and a affine variety. And from a affine, we will consider here this as a affine variety, then definitely an ideal. So now we have actually two maps.
Excuse me, I have a question.
Yes, please.
How are you sure that it is always non-empty?
Which one is non-empty?
This I of A.
I of A is non-empty. Okay. At this moment, I don't know. If it is non-empty, then it is an ideal.
Yeah, so we should put this condition that it should be empty. Sorry, it should be non-empty.
I will answer this question in a moment. Right? You will get your answer.
Okay. Okay, thank you.
Look here, because I have considered here A is not equal to Kn, right? So that's why you will always get that is non-empty one. But of course, I need to justify that one. That will I will do in a moment.
But we always have zero column.
Huh?
We always have the zero column in the ID.
This is
Zero
Zero
column.
polynomial in the end.
So it is not.
okay. So now we have here we have a collection of ideas. Because if it is empty, then definitely there is nothing to show that is it ideal or not. So still that is true. So you don't need to consider that property at all. So trivially that would. Okay, and there is we have affine varieties. In our affine space, right? So we have two maps actually. One is from ideal to affine, which is we will call this one B. So I can consider this as a map. So collection of ideals, if you will apply this map B, gives you an affine variety. And similarly from affine variety to go back, we can ideal, and that is nothing just I. This is our map, right? So you may ask a lot of questions here. What kind of questions? Are they inverses to each other? Right? So answer is yes or no? What do you think? Are they inverses?
No.
Because these are just function at this moment. I'm not putting any structure on that one because this is just a collection of ideals and just a collection of affine varieties. And now I'm just looking how I'm mapping to each other. So definitely they are not actually inverses of each other because of these things. If you will look the ideal, okay, if you have this polynomial x squared, and if you are looking the zeros of that one, this gives you just a zero element. If I'm looking this one in a fine line, n is 1 line here. And the polynomial is corresponding polynomial ring is this one. So this is actually, what is this one? This is nothing just the ideal of 0.
Zero.
Agree? Which is a 0 point here. And what is the ideal of 0? All elements, all polynomials will satisfy this condition.
X generated by X.
It is just generated by X. And this is not actually equal to your ideal I. From where you started? You started from this one. So this is not equal to this one. But one side it is one other way around is true, which is this one. If you have a variety, this is your affine variety, and you are applying the ideal of that one, and this is nothing, just gives you this one. So this is for all varieties. This is affine variety. And let's see why this is true. Because this holds always. Agree? So if you will pick any point here, then definitely that point will zero on all polynomials which are in this set. And by definition, it is trivial. So that's why this is trivial, and this is actually true for all, not only for affine varieties, it is true actually for all subsets of A and Kn, right? And for the reverse one, you need to definitely consider these affine varieties. So if you want to show that this is a subset of that one, so I will do this one by contradiction, which means that A is not a point here, and I will show that this is also not a point of that corresponding variety, right? So why, if this is not here, then definitely because this is variety, so I can write this one as a something, right? Because I said that this is a variety, so it is always a zero set of some j, which is here, right? So this is not here, which means that there is a polynomial in J such that f of A is not zero. Agree? By definition, because I'm not taking a point from here, so this means that there is at least one polynomial which is not giving the solution of this not zero at that point. But we know that because we know that this J is always here, right? So this means that f is in this ideal and f of A is not equal to 0 at this point. So this means that f is not, oh sorry, A is not on this one. Right? So that's why you get that this holds. This relation holds, but generally this is not true in general. Right?
You have a question?
Okay, yes. Is there any question? Yes, please.
Hello, thank you. I have a question. You have used two notations for V. One is a simple V, and the other is a stylish V. Is there any difference between these symbols?
Yes. Here V is actually a subset of affine space, and this V is actually the map. It's a mapping notation, right? Which is coming from this one to this one. Clear?
Okay, thank you.
Okay, now one may ask this question, what kind of ideals we have which satisfy this condition? So now my question is, for which ideals I mean, what kind of conditions I can put my ideal such that it satisfies this relation? They are equal because we know that they are not equal in general. But here you can see some connection between them. What kind of the ideal we could have? And that answer is that the ideal should be radical one. And what does it mean? Let me just recall that definition because it's coming from the commutative algebra. So if you have any ideal, then we can define this radical of the ideal is all those polynomials. Actually, it is defined for general ring, commutative ring. But here I'm just considering for this polynomial ring. So you are picking any point such that some power of f belongs to I. Let me write here. And for some n. So it's not necessarily that it definitely contains more elements than I. Because f power 1 is always in I. So everything which is in I is a part of this one. So it's more than that one. So that is called the radical of I, which contains all those elements whose powers are in I. Right? And what is a radical ideal? Radical ideal will be that ideal which is same as radical of I. So in generally we know that this is not true, but we will say that your ideal is radical if it satisfies this condition that it's same as radical of itself. So I is radical if I is equal to this one. And now we have the following theorem, which is actually the fundamental theorem of algebraic geometry, right? That is Hilbert-Nullstellensatz. We say that this thing which I have already said, that the ideal of the variety of an ideal I is same as not this ideal but the radical of I. Right? So this means that now you have this map. So let me write again.
I have a question.
Yes, please.
You said I under root is more than I. How it is more than I?
Because every element of I is already there.
Because in general, we think that if we take under root of anything, then it becomes less.
No, for example, I have here example. X here is my I and its radical is X.
Okay, thank you. Yes.
Okay, got it?
I have a question.
Yes, please.
Does this also show what is written on the left bottom? That the polynomials that define these zero sets are not unique? Does that also imply that fact?
Sorry, I didn't get your question. Could you please say it again?
So I am rephrasing that. For example, we have established that variety of the stuff that is written in the rectangular shape on the bottom left. Does that also imply that these polynomials are not unique, or are they unique up to something
Okay.
that describe the zero sets or algebraic sets?
Okay, I'm sorry, I have erased that part. As I said that if you have something like this S, and I said that this variety is same as the ideal which is generated by S, right? And here you can choose any set of generator of that ideal. So these polynomials are not unique. That's a very good question because it's a very important question to ask this thing, because later on we want to do this computation, then we will answer this question. And we will answer.
Okay. Thank you.
Such special set, which is actually called the Grobner basis of this ideal, and that is unique, right? So in generally the generating set is not unique. At this moment, the answer is that one, right?
Okay, thank you.
Okay, any other question? Okay, that's true, because I'm not going to prove this Hilbert-Nullstellensatz proof because it requires lot of time and lot of content actually. Which means that you need to recall all the really main part of the commutative algebra and some field theory axioms and a lot of stuff from that one. Definitely, I'm not going to prove this Hilbert-Nullstellensatz theorem at this moment, because if I will aim that one, definitely it will take like 3 to 4 lectures actually, if I will go in step by step to prove that theorem. So that's why I'm not going to do that one. But what we can see from the examples, it makes sense to you, right? So at this moment, just keep that idea with you, and now let's see what's going on in the rest part, right? Okay, so now we have a fine varieties here and radical ideas in our polynomial? No, I will go with again my maths, two maths. No, I can say that these are inverses to each other. Yes. Yes. Right? So yes, this
Arrow sign.
oh sorry. Yeah. So now I can say that this gives you actually the inverses of each other, because here I am taking an affine variety, it goes to radical one. And the radical goes to this affine variety. So we have this one is a inverses to each other, right? So this gives you a 1-1 correspondence map between them. Okay, now let's see few things which I would like to okay. So if you have your variety is just Kn, then what will be the corresponding ideal in that case? Can you guess what is that one? If it is a collection of all polynomials, then what is the point which satisfies that all equations are all polynomials? Actually, is
0.1.
Actually, this set is empty because we have the constant polynomials in them.
no, I'm here taking ideal.
I will just satisfy all these things.
All polynomials which satisfy those points. Actually, sorry if I said before wrong. So you need to find all those polynomials, right, which satisfy all these elements, which is just a
Zero polynomial.
zero polynomial, and that's great. Okay, so now we have this 1-1 correspondence between these two things. And if you have here this ideal, then definitely its corresponding variety is this one. Agree? Which means that you need to find all those points which satisfy this polynomial. So definitely zero polynomial is already giving you zero. Whatever you find, you will pick. Right? So that's why you can go back here again. And now, if you will have this one is nothing just empty set. Then what you will get here?
The whole thing.
What will be the ideal of this one? I can see the also in the chat box too. If you want to write your answer, you can write your answer in the chat box as well. Right? So if you have a affine variety, which is just empty set or a set have at the beginning, what is the corresponding ideal? And you need to find all those polynomials.
Satisfy nothing.
So this means that this is nothing, just the whole polynomial, because there is no point. So this means that the common zeros of this set is actually nothing, is empty. Okay, let me just add one more step here. If you have just a singleton, what is the corresponding idea here? Okay. If you have just single point here, the corresponding corresponding ideal contains.
It will be the ideal generated by the polynomials of form xi minus ai.
Yes, that's true. So this is nothing, just equal to generated by x1 minus a1, x2 minus a2, and so on, xn minus an. And you remember what kind of this ideal is?
Maximal ideal.
It's always a maximal ideal. So if you will look, if I will restrict this one to the maximal ideal, then what you will get here are affine varieties. These are just points. Right? So points corresponding to the maximal ideals, and maximal ideal gives you points. Right? Okay, that's great. So these are just giving you points in here. And the corresponding point is very clear from this correspondence.
Is it true that every maximal ideal is the radical ideal?
Is every
maximal ideal real?
yes,
Yes.
it's a prime.
Yeah.
Every maximal ideal is prime and every prime is radical. Right? Clear? Because we have this power is in I, and if it is prime ideal, then definitely F must be in I. So that's why it will have this property. But I'm using here every maximal is prime, so that's why.
Another justification is that if I is not radical, then the radical will be maximal, so they the convention.
I is not radical, then definitely
Radical I will be maximal ideal.
yes. No, radical of maximal ideal.
If
No, I will answer that question what you have asked already, right? So let me just give few times, so that definitely I will answer those questions as well. Okay. So this is, so far we have seen this dictionary at this moment, algebra versus geometry. That's why you have this commutative algebra, which is just giving the algebraic picture of your varieties here, right? And now we will see some geometry or some topology on your varieties.
What is the good book to read?
What is the?
Good reference book.
Okay, it's a little box I will give you in the end at time. Little Fox, or you can, if you want to go to the Hall-Schenk's book, which is algebra, applied algebraic geometry book, or if you want to go more advanced, then definitely there are a lot of books like Sheveridge and lot of stuff. Okay. So now what I said that now we will discuss some topology on our varieties. Right? So let me just. So we have this affine space. As so far we don't have anything. What kind of topology? But we know that some properties of topology. So let me just recall some data. What we have done so far at this moment. So if you look all the data, we have seen that these affine varieties satisfy some certain conditions, some certain properties, right? Very first one is empty set and affine space itself, they are affine varieties. Agree? They are affine varieties. Another point which we have seen that is finite union of affine varieties is affine variety. Agree? We have seen for two, but we can extend it to up to finite one. And the last one, infinite or finite, we have whatever you want to say, infinite. Instead of infinite, I will write here arbitrary because it's also satisfied for the finite case as well. So I will write here arbitrary. Intersection of affine variety is affine. Right? So we have already seen these three properties of affine varieties. And if you know some topology, some basic definition of topology, this says that we have a topology on Kn, which is where closed sets are nothing just affine varieties. So I can define a topology on my space through these algebraic affine varieties, right? Which are nothing just a closed set. Because if you know a little bit topology, then we know that there are some collection of closed sets, there are some collection of open sets. So if open, we will call sets which satisfy these certain conditions, they are called closed one, right? And this has a special name, this topology, which is called the Zariski topology. So this is actually the Zariski topology on affine space. So now we will talk about little bit more about topology of our set or of our fine space. So on Kn, we define topology as closed sets are affine space, affine varieties. Right? So we have defined our topology in this one in case that what is a closed set in my topology is an affine variety, right? And this topology is called Zariski. Right? And what is the Zariski topology on any set? We can define a topology on any arbitrary set of affine space. It's just induced by this Zariski topology, like a subspace topology, right? Okay, that's great. Now let's see some basic facts about this topology, right? So if you have affine variety, so our subset let me call subset V of A is closed. What do you think? When it will be closed in your given affine variety? If and only if it is closed in affine space, in whole affine space, right? So this is the closed property which is coming through this setup, because our setup is true defined through the closed set, so that part satisfies the closed property because this is already closed here. So the closed, if your set is already closed, then definitely a subset which is contained in that one that is closed, if and only that is closed already in a bigger one. Right? If you already defined through an affine variety, then you will just take the intersection of that one with your affine pair and nothing else. Right? But this property is not true for open sets case. So if you have some open set, which we will call the Zariski open set, in your affine variety, if that one is open, that is not necessarily that will be open in your whole variety. Right?
No, I didn't get this.
Sorry?
I didn't get this point. Let A be an affine variety. And capital A is.
A subset V of A is closed if and only V itself is closed in K, which means V is closed in K and what is the meaning of that one? That is coming from some, is a zero set of some variety or some polynomial. And definitely what will be in that? Okay, let me just write this connection. And this contains actually all the elements which are here, here as well. Sorry, here as well. In A. Right? So let me just, okay. Suppose we have this thing. B is closed means that this is true, right? And what does it mean? Because A itself is an affine variety. So it's coming from some collection of polynomials. Yes. So definitely this is nothing, just a collection of all this size. And this is again an affine variety. So that's why it's an affine variety. Because this is always contained in it. Right? It's just an intersection of that part. But as I said before, that is not true in general. I mean, for the Zariski open set. Yes. I have already given a lot of example about that one. So if you have, for example, I will just recall my previous example. Okay, let me just go with that one. I'm considering here A, X, Y, which means in two determinants. So I have one. One affine variety is this one. What is that one? It's just a line which contains all points of this type. Agree? And if I will take this one, so it's just a Y. So if I will just like, if I want to draw that one, so this gives you nothing, just this is your disparity, right? And one Y is disparity, which is this one, the above one, right? And what is the intersection of that one? Definitely, when you are looking the zeros of this one, is a bigger set. And you want to solve this one for more polynomials, which means that more polynomials will satisfy those solutions, then definitely your set is going to be reducing. So that's why you have this relation here. So this is ideal. Sorry. You have I is contained in J, then the varieties is definitely just satisfy this relation, opposite. Right? Agree? So that's why you make it. And you will see the intersection is coming this one. So if you want to see what is this variety, this is nothing, just this single time. Right? So is it the answer of your question, Bahar? Because whenever you are increasing your set, right, then variety will be smaller one. Like here you can see in very simple example actually. Right? So if you will add more polynomials here, then definitely it will be going to be very, very smaller. We satisfy both of them. So that's why you have this idea. It's a reverse relation here. Okay, no. So if let's move on. So as I said before, this property does not hold for the Zariski open sets, right? But one more property I would like to mention, that if something is closed under the Zariski topology, this means that that is also closed in the usual Euclidean topology as well, right? So if some set is closed as a Zariski topology, in a Zariski topology, then definitely it will be closed in the Euclidean topology as well. So what is the reason of that one? Because polynomials are continuous functions. And when you consider a variety here, the pre-image of that one, the closed one, the pre-image is also the closed one. Why? Because that is just the pre-image of the zero set. So that, and you know that the functions are continuous, that's why it satisfies that condition. Right?
We have another question.
Sorry? Yes. yes, if I is a subset of J, then the variety of J is subset of, yes, that's true. We have seen here, right? Okay, now let's move on. Okay, there is another notion you have already seen in a topological spaces, that is the connectedness. But here it is not interesting for us at this moment. Why? The reason is that one, for example, if you want to look this variety, it consisting of 2 points, 0 and 1, right? And here you can see simply 2 disconnected components of that one. If you have a look at the topological space, then that's true. But for example, if you want to look this one as a topology, I know that this is nothing just equal to the union of, sorry, the intersection, union of these 2 varieties, right? But they have non-empty intersection, which is a 0, 0 point, because this variety is nothing just these 2 lines, and this intersection is this one. In a usual topological space, as a connectedness, if I will use the connectedness, then definitely these are not disconnected. This is connected one. But in our setup, we need something which describe this one as a 2 component, right? So what does it mean? That you will call the irreducibility, right? Not the connectedness. So I will define that one. So a topological space, so I'm just giving here the general definition. So a topological space is reducible. It's not irreducible, but reducible if it is empty or there are closed sets of X such that X is the union of these closed sets. And furthermore, these closed sets are not equal to this bigger set. They are actually the proper closed subsets of X, right? Then we will say that that is reduced, like in this case, this is not irreducible, but it is reducible. Otherwise, we will call that space is irreducible. Whenever you don't have such kind of closed sets which satisfy this condition, then it is called irreducible. Right? So here we have this one is reducible. Right? Okay.
So there is no condition on X1 and X2 that both are disjoint or not.
They are just closed subsets of X. And they are proper one. And of course, if one of them is equal to X, then other will be empty one. So we are avoiding those closed sets. Other than, so that's why I said that proper closed sets. Right? Like here. This is reducible. Because this is closed and this is not equal to this one. This is closed, this is not equal to this one. Agree? Okay. Now let's move on. So here I will go with another example, which we will see that that is reducible or irreducible. How we can check that one. And later on we will describe or put the condition of your ideal, corresponding ideal for which your variety is irreducible. Right? But before that one, let's consider this example. So you will have better understanding of your closed sets. Right? This is your variety. k square. And my question is it irreducible or not? Right? So how you will answer this question? So what will we need to do that? For the reducibility, I need to see that what are closed sets of this variety. So let's call it H at this moment. You know that what is this one?
This is graph of y equal to
If I will just draw this one in a real plane, not the complex one, remember, because whenever I'm drawing in a real one, real space or real plane, because I can't draw in a complex one, then definitely you know that this is nothing, just a hyperbola. Agree? And it seems to you that it has two connected. I mean, it's like reducible. It seems to you. Seems. But that is not just, this is just a real case actually. This is not a complex case. Right? So first of all, if you want to see that this is reducible or irreducible, we need to see that what kind of closed sets of this variety. Right? So we will try to understand the closed sets of this variety. So let's pick a proper, not only the closed, but there must be proper one, proper closed subset of H. Let's see what kind of this set is. So we can answer this question, it is reducible or irreducible, right? So now you can see that because I said that this B is properly contained in H. So this means that there is at least one polynomial which is 0 on B, but not 0 on this one. Yes. Right? Agree? Because it's properly contained. So this means that there is a polynomial such that f of xy is 0.
0 on V.
0 on V. But not 0 on X. On sorry, H. Right? Agree? For all, whatever the point you will pick, then definitely it's not 0 on that. Okay. So because we are saying that,
There is some points which are not.
so because we know, yes, because we know that this is true, B is a subset of H, which means that this, the point which we are considering here that satisfies this one as well. So that's why if I will picking a coordinates or a point in B, this means that B, because satisfying this H, which means that x, y is equal to 1. So I can write here that y is equal to 1 over x. Right? Agree? Yes. Because I'm just looking these coordinates in K2. So this means that this polynomial, if I'm considering this polynomial, I can consider this polynomial as well. Just replace y with 1 over x. Because if this is a solution of that one, then definitely it satisfies this one as well. Right? And because this is not 0 on H. So this means this polynomial is not identically 0 on H as well. But what is this one? This is a single polynomial in X, which has some negative exponents as well. Right? So this is not a polynomial actually. This is something, you will get something like that. Agree? This is something like polynomial. This is something like you are getting some exponent which are negative as well. Agree? Right? So what we will do with this polynomial, because we know that this polynomial is never zero on age. So if I will pick the maximum such j, right? Like for example, if you get this polynomial like in this way, for example, x squared plus y squared, because we are just working in two, oh, sorry, not y squared, x cube, and you are appearing here some negative coefficients, and blah blah blah. Let's end up that -7. So this 7 is the maximum which is appearing in the negative part here. So then if I will multiply this polynomial with x, so let m is such number which is appearing in that one. So this, if I will multiply with this one, with this polynomial, what I will get? If I will multiply this polynomial with x power 7, this will become a polynomial actually. So this is nothing, just a polynomial in one variable. Agree? So if it is a polynomial in one variable, then what will happen?
This G is the maximum power of y appearing in that.
Yes, this m is the maximal power which is appearing in the negative part. Like here in this example, 7 is such kind of number, right? So I'm multiplying this polynomial with x power 7 to get up indeed a polynomial. So now you have this polynomial in one variable. So what do you know about a polynomial in one variable? How many solutions does it have?
Slightly many.
Huh?
Slightly many.
Finite many. It's depending on the degree of that polynomial, but we know that they are just finite many. So this means that this polynomial has only finite many points. Which means that because this has only finite many polynomials and this is giving you 0, so this means that that point which we are coming from here, v, so v is always a finite one. Because we are just getting this coordinate x, but y is depending on x. So that's why if you are getting just finite many solutions for x, so this means that v has only finite many points. So thus, v has only finite many points. Because these points are depending on this variable x, first part. Because the other part is just coming from this relation, right? Finite many points. Okay. Yes, there is a question. If you have polynomial and use max, then sign method. What it should say? Yes, because here I said that this m is such that this is the largest one. This is appearing there in your polynomial. You have to choose, for example, I have written this polynomial. You have to choose this x power 7, not like x power 3 here. Because here 3 is the degree if you will look in positive way. But if you will look the least, whatever you can say, the least exponent, that is the x power 7, -7. Right? Okay, why I have chosen x, y is equal to 1? Because we are here. And age is this one. Because whenever I am picking a point, it must satisfy this relation. If you want to see that what is this one on age, then definitely it satisfies this relation.
नेक्स्ट पार्ट है तो इधर देख लो नेक्स्ट पार्ट में स्ट्रेट
Sorry, could you please repeat your question? Okay, so this means that you have just finitely many points in your variety B. So what you get? You get that using proper
लिख लो तो इतना टाइम तो नहीं लगना
right?
तो कहते कोई
So if you and B is a proper closed set, then definitely it has only finite many points. So now think about that one. can you write your H as a finite union of these proper closed sets? If you can write, then definitely you have here finite many points. And finite union gives you just a finite set, which is impossible because H contains infinite many points. So this means that H cannot be write as a union of proper closed sets. So that's why it is not reducible. It is actually irreducible, right? So because since H is finite, so it is irreducible. Because every proper subset contains only finite points. And if you will consider the finite union of closed sets, then definitely you will get finite one, but it not covers whole page. Right? So that's why your H is irreducible. Okay, now we will answer this question as I said before. We will just see what kind of ideals we will have, which gives you actually the irreducible varieties.
Excuse me, Shaheen. Sorry.
Yes, please.
Can you hear me?
I'm confused about how we have infinite points. Ma'am? Yes.
No, V has only finite many points. V has only finite but many points. Okay, why this is true? Look again. We are picking a point in B, which means that it satisfies this equation because that is a part of H. So this means that that satisfies this equation, right? So this means that you just need to focus on one variable. The other variable is already fixed. So that's why you get here a polynomial in one variable, but definitely here you can see that some negative exponents will appear because we are choosing here 1 over x. Whenever y is coming in your polynomial, then definitely you are getting some exponents which are negative. So now you have to choose this least, you can say the least negative point, right? The smallest number. So minus m is that smallest number, you can say that. And you are just multiplying with that one. So you get a polynomial here because you want to see the solution of this polynomial when it will be 0. So this will be 0 if and only if this will be 0. Although on those points, because you just need to put just x, just one variable. And if you want to say that if it is 0 somewhere, then definitely it will be also 0 somewhere. It's the same point actually. Because we are just multiplying with x power n. Right? And you can say that here might be possible that it's 0 when x is 0. But if x is 0, then definitely it's not satisfying your H. So definitely here x and y are both are non-zero.
Excuse me, Shaheen.
Yes, please.
May I ask a question?
Yes, sure.
There is something strange here. You showed that every closed subset of H has finitely many points, actually. But I mean, H as a closed subset of itself has finitely many points, right?
Subset.
But you haven't used the proper condition here. You just consider x and y in V, and you show that there are only finitely many.
I said that I'm picking that polynomial which is 0 on V, but not 0 on whole H. We have such.
Okay,
So we are working on this polynomial actually.
just for a moment, does not consider the last line. I mean, f of x and y is not 0 on H. Then your argument works again here. So, I mean, you show that every closed subset, even if it is proper or not, has finitely many points. But this is not true because
No, as I said that because I'm choosing V is the proper subset, so I'm working with that polynomial which is non-zero on H. So this is not identically 0 on H. Because the points which you will get for that polynomial, then definitely that will give you whole H. And we are not considering that case actually.
oh, okay, yeah, that's right. Yeah, sorry. Thank you.
I'm not considering that polynomial which gives you, this means that I'm not considering this x, y is equal to -1. I'm not considering this polynomial. That's why you have such kind of polynomial which definitely will appear, which satisfy all those conditions. So that's why this will just giving you a solution like a single polynomial in a single variable, which just has finitely many points. So that's why this proper subset, closed subset has only finite many points. It is clear, Ali?
Yeah.
Okay, that's great.
Thank you.
Thank you for your question for more clarity. Okay, is there any other question?
Yeah.
No, I'm not saying that when we will multiply this one, this function will not change. Definitely it will change, and that will be just a polynomial in a single variable. Now it's a polynomial. Before that, this is not a polynomial in one variable because here you are getting some exponents which are coming with the negative exponents. No, we are making this one into a polynomial by multiplying this one. And what is your question, Abdul Razak? F of x. Okay, the same one. Okay. So now it is clear. Okay, why are we now multiplying this step there? Because we want to look the solution of this one. Yes, that is the answer which we have seen in the chat box as well. Because we are looking the solution. What are the zero set of that one? So it's just depending on this x actually. How x we are performing here. So this will be the zero. So the zero of this polynomial and zero of this polynomial. Sorry, this is x power n. So both have the same zeros. That's why we are just considering here. If you will find a point here, x1, let's suppose, that gives you 0. Definitely, it will be 0 here. And this will give you a solution of this. This gives you a point here. Yes, Farah?
By having the same zeros, you mean the same number of zeros or exactly the same zeros?
Exactly the same zeros. Okay, so for example, if you have a 0, 1 0, let's suppose x1 is a 0 of this polynomial, then definitely it will be 0 of this polynomial as well. Agree? Okay, you may think in this way because we have a polynomial in 2 variables. So we have just fixed one of the variable, right? And with some computation, we make a polynomial in 1 variable. So if you want to see the solution of this polynomial, then definitely these are the solution of the original polynomial. Agree? Because in original polynomial, we have this setup, which is omitting 0. X is equal to 0 and y is equal to 0. So this is the only 0 can coming from here, which is not gives you 0 for this one, but 0 for the whole polynomial, but we are not counting that one. Agree? Okay. Let's move on. So, as I said before, so we are looking at an affine variety V in our affine space is irreducible if and only if corresponding ideal is prime. Agree? Because now our B is not splitting in two parts of closed variety, then definitely here we will get this prime ideal and the vice versa. You can do, it's a very simple exercise in a commutative part. You can do this one by itself. So prime, you know that what does it mean? If you have the product which is in your ideal, then definitely either the product of two numbers, one of them must be in your ideal, then it is called a prime. Okay, now let's see some example which might be answer your question. So you have some polynomial, right? And you're looking for the zero of that polynomial. And this variety has some special name, it is called hypersurface. So if your variety is defined by a single polynomial, it is called a hypersurface. Okay? And we know that little bit about this polynomial ring, which is UFD, unique factorization domain. So every polynomial can be factored into irreducible parts. So this means that I can write this polynomial in this way, where FIs are irreducible polynomials. And you know that irreducible polynomial is giving you always a prime ideal, which is an ideal which is generated by irreducible polynomial is always a prime ideal. So I can write my F in this way. Because here doesn't matter I'm writing the power of F or not, because it's giving the same result. As a variety, they are the same. So you have this thing. So you can see that every hypersurface can be written as irreducible of these hypersurfaces. So I will just write here this one as every affine variety. So we can generalize this idea because here I'm just picking a hypersurface, but we can do this one for every variety. So every variety can be written as finitely many irreducible closed subsets, which means subvarieties actually. Right? Affine subvariety. That is, you can always write in this way. Yeah? Yes. And these are irreducible ones. But this, when we ask this question, these irreducible components are unique or not? So what do you think?
They should be
Yes.
unique.
Huh?
Yes.
They should be unique.
They should be unique, but it's not necessarily. Let's see an example. It's just a trivial example, which is just this one. You have already seen that one. It will be unique if we will put certain conditions on those setup.
If they are in RTP.
Whatever you want to write, you can write infinite many points as well. Agree? Because this point is here, this point is here as well, this point is here as well.
Yeah, if one is not contained in the
Yes,
other.
so we will put some certain condition to give the uniqueness. Okay, so there is a lemma which says that yes, you can write in a unique way. So this is an affine variety, V. Then there is a unique finite set of irreducible polynomials, collection of irreducible polynomials, not irreducible varieties. Closed subsets such that first one is the union is equal to that one, definitely. And the second one is that none of them is a part of the other varieties. Right? So this condition is important here. This will not allow you add something like that because this is already here, so we can omit that one. Right? So these gives you actually the maximal irreducible parts. Maximal irreducible closed sets actually. Right? This is fine. This is irreducible. This is irreducible. But this is not maximal because it is contained here. This is not maximal because it is absolutely. Yes, there is a question. Why are you doing? Where I have written this one. In this example, I just put some numbers which satisfy these gives the variety. That's it. Right? There is no certain condition, but I have chosen these numbers which are actually in V actually. You can write 0, 4 as well. Right? Whatever you want to write, you can write here. I have just shown you that this is not unique if you will not put this kind of condition. Right? So in this way, these are the maximal irreducible subsets of V. You have chosen in your setup the maximal irreducible set, which satisfies all the set.
Ma'am?
Yes.
Okay, we are known that finite union is always variety.
Just a minute. This is not H, this is 4. Okay, sorry, yes.
Okay, so finite union is always a variety, but
Finite
union of variety is always a variety, but maybe infinite union may be a variety. It can be.
Yes.
Okay, so what thing it shows that there are only finitely many irreducible components.
There are only finitely many. Okay, I will answer this question. This is by using the Hilbert basis theorem actually. So why we are coming this setup?
Okay.
So there is corresponding setup in the ideal setting, which is called the primary decomposition. Right? So if you want to know that why you will have always finite collection or why you will have such kind of varieties, and we always have these are maximal one. So the answer is of this question is that is coming from the ideal part, which is actually the corresponding setup is called the primary decomposition of ideals. So if you have a prime ideal, then it's everything is fine because the corresponding variety is just a irreducible one. So if your ideal is not prime, then you want to look the primary decomposition of that ideal.
But here is only one polynomial. One polynomial. But here is only one polynomial.
But
So
in generally, you don't have one polynomial. You have a lot of generators which are only finite one.
yeah, but I have a question about only one polynomial. So if we are
So this is clear here. So you will have just finite one because I said that F because your ring is UFD, which means that
unique
factorization of the domain. So if you have just finitely many components in this way.
Okay.
This is trivial here, and that's why this suggested us something here. Here it is not necessarily that V is a hypersurface, but if it is a hypersurface, then it is very easy to see this property. But it is not a hypersurface, then definitely we have something which is generally true. Okay, so let me just close today's lecture at this point that this is true due to the primary decomposition of primary ideas, of ideas. So let me just quickly recall what is that one. So if you need to go back to the commutative algebra, you can just recall that what is actually the primary decomposition
I
is.
have a question.
So what is your question?
What is the difference?
What is the difference between V and stylish V? Okay. V is just a set of our affine space, and this stylish V is actually the map which we are applying here on some polynomials, which means that this is the collection of all points which satisfy this equation x, y is equal to 0, or the zeros of, you can say that the zeros of this polynomial. I have already answered this question as well. Okay, closed set means that this is closed set as in a Zariski topology, which means that it's just an affine variety. So closed set is just an affine variety. If you're looking affine variety in some affine variety, that is also called a subvariety, and also you can say that that is a closed subset of V of an affine variety. Okay. Not mapping from X to Y. If you remember, I have written many times this setup. You have here affine varieties, sorry, polynomials, because I'm taking here ideals. And here we have affine varieties. So this is giving you a map from here to there, right? So you have here ideal, and you are applying this operation. This gives you all those points in your affine variety, affine space, such that f of A is equal to 0 for all for all f belongs to I. This is the definition of this stylish V. So closed set, a closed set means that that is again a variety, definitely a solution of some polynomials. Yes, that's true. So we have, so let me just recall quickly what is the primary decomposition. So if you have an ideal in your, let's suppose we are still in our polynomial ring. So this ideal can be written as in the intersection of the ideals, which are actually Qi's are Pi primary ideals. And if you have this setup where Qi is not contained in, does not contain the union of, or the intersection of J is not equal to I. Then this one is called primary decomposition, and this is sort of called the unique primary decomposition in this setup, right? It's not really unique in the sense that QIs may be different here, but it's a unique in the sense that the corresponding P, because these P's are here the prime ideals, that will be unique in your primary decomposition. Right? For example, yes.
We call the definition of Pi
This?
primary. We call the definition of Pi primary.
Okay, so primary ideal definition. Qi is primary. Right? If you have X, Y, let me just write FG belongs to this one, your A, such that this product is there. This implies that either F belongs to Q or some power G power belongs for some N. And what is P here actually? Because this is not prime ideal. So if you will take the radical of this one, then it is actually the prime ideal. So that's why it is called PI. Corresponding radical ideal is prime ideal, so that's why it's called PI prime ideal, right? And what is the connection between here the maximal part and the here prime ideals? For example, so let me just give the example so that you can really understand what's going on. So for example, you have this ideal. I can write this ideal in this way. You can also write this one as a decomposed position in this way. So here you can see that these two compositions are not unique, right? But here, these are all primary ideals. This is actually the prime ideal. So primary, definitely they are primary, but these are not primary ideal. But if you will look the radical of this one, this is nothing just x1, which is prime ideal. And same is true for this case. So my uniqueness means that these ideals can be different, but the prime corresponding prime ideals, they are unique. In both cases, you can see that this is true. So this is called the primary decomposition of your ideal, right? And what is the uniqueness in that case is that one, the corresponding prime ideal, actually these are called also the associated prime ideal of your ideal. They are unique because here you can see that the corresponding associated prime ideals, they are just x and xy. This is g power n. Either this is true or this is true. So if you really want to see that, I will suggest you some commutative algebra book. You may see and you can find this setup in primary decomposition in that book for more details. Yes, it is the definition of primary ideal. It is for some n. It's not necessarily n. It's a part of definition actually. Right? Okay, so if you have any questions from today's lecture, please ask because I'm not going to do anything new at this moment. So, but I will answer your questions at this moment. So appears that if you will unmute yourself and you might ask some questions, it would be better for you. Might be possible I have missed some questions from your chat. Okay, so let me just. Okay, so you can see the book's title. I have already uploaded on the abstract. If you will go to the website of Simba School, there you can find the list of books, right? But if you don't have those at this moment, so let me just try.
बता दें टाइप कर देते हैं
Sorry,
बुक का नाम बता दें टाइप कर देते हैं
वही मैं कर रही हूँ. This is the very first book, Cox and Litter, by Cox and Litter. Ideals, Varieties, and Algorithms. And the other book is by, it's a computational algebraic geometry. By Paul Shin. There is another book by these three guys, which is called the Using Algebraic Geometry. And that's it. There is also by Smith and the other authors is an imitation of algebraic geometry. There are few other books to make not from the website as well. Okay. What is your question actually? Abdul Razak, I said before, if you will ask, what is Q? Here I have defined the definition. Okay, let me just write here Q. So I think it will be easy for you to check. Okay, what is the definition of Q? Q is some ideal, Q is primary. So this ideal is primary if it satisfies this condition. Yes, the risky open set is actually the complement of closed algebraic set. That's true. Excellent. I will go very fastly to revise these concepts, because if I will go just in this way, then definitely it will again take whole lecture. Then definitely I will just briefly describe what we have done in the first lecture, and then we will move on to the next part, the new topic, right? Because so far we just have seen varieties, how they are linked with the algebra part, how you can move that one, how the topology is acting on that part. And now later on in the next part, we will see that if you have two varieties, how you can define a map between them and further more properties. Yes, definitely the recording of this lecture will be available on the website of SIMPA. So have I answered your question, Abdul Razak? This is not a usual lecture. This is just the introduction of that course. So it's a pre-courses, and usually they are fast pacing. It's not the usual semester lectures.
Thank you so much. Will there be any follow-up lecture?
Yes, definitely. We have 3 lectures. Yeah, till Thursday.
Okay. It means there will be another lecture tomorrow or another day. We will receive an email.
Tomorrow same time. Tomorrow same time lecture.
Oh, sorry. We have the same time at 5, right? From Monday to Thursday.
Okay. This was the first. This was the first one.
This one is the first one.
Okay. Thank you.
Weekly questions are in hands out notes are provided.
No, at this moment I don't have any handouts. Okay, any other question?
Yeah, this recording.
Yes, this will be available.
Where?
Yes, you can join through the same link. What is a fine variety? It's just a zero set of your polynomial. So ऐसे points जो polynomial को satisfy कर रहे हैं, that is the Riemann answer. Then we should give a bit.
Hello. After these questions.
And
I have one question. You have? Yes.
Okay, you can share. Okay, one of my student has the handouts of today's session. She will share it with you. Okay, as I said before, when I defined a fine variety, I said that in some books like Little Fox Tree, they are using the notion of a fine variety as I have defined is a zero of some polynomials is the same as algebraic sets in some other books. Right? So it's all depending on you that how you are describing this thing. So you are saying this one as an algebraic set or an affine variety. Thank you, Ari. As I said before, next session is tomorrow at 5 p.m. at the same time when we started today.
with same link.
That was the bigger question I I don't know what is his question. I know I have tried to answer all questions, but I don't know what is missing. As I said before, Abdul Razak is
Asking
a polynomial. Are there polynomial in a fine variety? No, a fine variety is a subset of a fine space. It's a very simple example. I have given at the beginning like a circle. Like you have done the linear algebra. Let's forget about any polynomial. Let's talk about linear equations. Right? So you know that if you have system of 2 by 2 equations, which means that you have two polynomials. Yes, that is called just in a linear space. When your polynomials are linear, then definitely it is called a vector space and the corresponding matrices, and you are getting all the data. But here we don't have. So we have considering more general polynomials. They could be 2 degree, 3 degree, and more degree. And definitely then we are using the concept of vector spaces, which is the linear one. Okay, so I think so. I'm just stop here. If you want to be here, Abdul Razak, I will answer your question very slowly, right? So if someone else really want to stay here, he or she should stay. Otherwise, rest of the people can leave this meeting. And Abdul Razak, if you are here, then definitely I will answer your questions.